Invite Ling Feng.
Hi.
Hi. Would you please share your screen and start the session? You have 12 minutes. Please be on time and 3 minutes for discussion. So
Okay, sure.
we can start whenever you are ready.
So, okay, let me just check the time. Well, hi, good afternoon, everyone, and it's evening here in Singapore. So yeah, thanks organizer for giving me the chance to share our recent findings and knowledge at this CCS conference. So I'm Dr. Feng Lin, or Ling Feng. So my surname is Feng. I'm from two institutions. One is Institute of High Performance Computing in Singapore, and also I'm also in the Faculty of Physics at the National University of Singapore. So that's why my work deal with both computations and physics. So today I'll be talking about the information processing at the edge of chaos for generic nonlinear systems. So I'll be going through a fair bit of stuff, but many of the background story I'll be breezing through really fast. So I'll be starting to talk about a little bit of the previous old findings in the brain about edge of chaos, and also the order chaos transition in simple single layer neural networks. Then followed by, of course, the very classic well-known result of logistic map. Then followed by actually our empirical findings in numerous deep neural networks, the latest deep learning networks. Then at the end, I just present him a theory of information processing for generic nonlinear systems. So yeah, so it has been well studied that also empirical evidence that actually has been hypothesized, I would rather say. The brain seems to be operating near some kind of critical state. And yeah, there's all kinds of empirical evidence suggesting it. And this kind of criticality, I mean, there are many kind of critical phase transitions, right? And there are several types, but this one particular, some people propose that it's the transition from order to chaos. So of course, there's like empirical evidence on that. Then in the 80s, 90s, people trying to understand for neural networks, because brain is a neural network. So if you simulate a neural network, what's particular about the edge of chaos? What's happening there? So there has been numerous simulation evidence showing that the information processing is the most optimal at the edge of chaos. So people have done like a single layer, fully connected neural networks. There has been also recurrent neural networks, but they are mostly simple structures. So you do see that there's some critical lines, and when the system is operating on this critical line between order and chaos, it seems that information is maximized. And there has been some theoretical improvement understandings on why this is the case for this particular simple layer neural networks that is fully connected. There's been, yeah, and the progress is going on even in the recent years for this single layer neural networks. So just to get a visual picture of what exactly is chaos, we can just adopt the very famous example of logistic map of this quadratic equation, where you iterate it 100 times. So you can assume that output is at 100 times of iteration is the output, and the input value between 0 and 1 is x. So you can see the bifurcation process, right? You do see like a bifurcation, period doubling bifurcation, and then it goes into slight chaos, and the system gets more and more chaotic. So there is a period doubling bifurcation until chaos sets in. Of course, there are other intermittent bifurcation processes built in between this big chunk of chaotic phase. In the end, yeah, when the R value increases all the way until 4, then it will just be totally chaotic, as you can see here. So this is a well-known result. We just put in a different perspective. So this is the input and output is just all over the place. It's chaotic, right? So what you can do is you can That thing doesn't go away, huh? So you can also say for different R values, you can plot the iteration with the value of X versus time. So there are two different colors here. One color is the original value of X, and the other color is the slightly perturbed initial condition of X. So you can see that the two always track with each other means they're ordered, right? So when they are just all over the place, they're different from each other, it means chaos. So this is the period doubling process. And then here about like somewhere here, the period doubling ceases and chaos sets in. So this is a typical transition from bifurcation, stable bifurcation order to chaos. So actually, in modern neural networks, you do observe exactly the same thing. So what we did is we carry out a multi-layer, fully connected, they call it a multi-layer perceptron neural network. So we trained on one of the most famous benchmark image data set, which is just, they call it fashion MNIST. So it's a bunch of images, there are 10 categories. If you train it, if you take this part as a dynamic operator, and at every time, so you train it many iterations, many epochs, they call it. So that at each epoch, you can take out this bulk of the neural network and treat it as a dynamic operator. You can find the evolutions. You'll see that actually it also it shares a close resemblance to what logistic map has done. Initially, it's a single fixed stable fixed point. It's just like sometimes you have double periods, sometimes you have 4 periods, but in the end, it goes into chaos. So actually, you do see that actually this kind of very complex structure it's not really complex, it's complicated because there's many neurons, many layers. It shares a close resemblance to what is happening in the logistic map. So of course, it's well known in chaotic systems that you can make a point correct plot to visualize what the system is doing. So you plot xt plus 1 against xt. You have a single fixed point. You have a two period cycle. You have like this is 16 period cycle until you have edge of chaos. It's a lot of cycles until you have total chaos. So the blue background is like single fixed point. The green is stable periodic cycles, and the orange is referring to chaos. And this is the well-known edge of chaos for logistic map. So if you do the same thing for this multi-layer perceptron neural network trained on the image data set that everyone else also uses, you actually do observe this kind of bifurcation process as well. Single stable fixed point, it bifurcates into a loop of about 8 to 10 period cycles. The period cycle increases into a very dense period. And in the end, after it passes through this phase transition, it goes chaotic. So yeah, so they do share a lot of resemblance as well. And what is interestingly is because we trained on the real data set, we know that when the model is most optimal by looking at the test loss. So you do see that from left to right, as the model trains, the test loss decreases to the most lowest point at the edge of chaos. Means the neural network transitions from a periodic stable periodic cycle to chaotic phase. And then after that, once it becomes in the chaotic phase, actually the test loss increases, which means the model actually performance degrades. So the red line is some theoretical result I'll be talking about later, but for now you can just remember if the symptotic Jacobian normalized by the 1 over square root of the dimension, when it's 1, it means it's edge of chaos. So how about even more complex neural networks? Because there are like in the recent years, the computer scientists have developed more and more complex neural networks. So you can see there's convolutional neural networks, but it's still layer by layer, but they even put in like a LXNet, and there's like DenseNet where they introduce a lot of skip layers. So what we find is, regardless of the neural network architecture you're looking at, they are always the most optimal at the edge of chaos, interestingly. So this is the same case. The neural network, as you train more and more for convolutional neural networks, it goes through these 3 phases, and the optimal point is between this periodic cycle phase and the chaotic phase. So if you implement it, even the state of art, not just the architecture, if you also implement the state of art training algorithms to prevent overfitting, and what you observe is that actually the model keeps getting closer and closer to the edge of chaos, and it oscillates actually in these three phases. This is single fixed point and periodic stable periodic cycle and chaotic phase. It oscillates among these three phases almost indefinitely as the model gets more and more optimal, which means the training accuracy keeps increasing, where the testing loss keep decreasing. So this is actually quite interesting. We also tested on even another state-of-art neural network, deep learning architectures, deep neural networks, and with more also the state-of-art training algorithms. So the same phenomenon is observed. It starts from the chaotic phase, but then it somehow settles to this frequent transition between these three phases. Actually, if you look at it closely, the fact that actually the model doesn't change too much, the weight doesn't change too much from this point onwards. So that means the periodic cycle phase is extremely narrow. That's why the model can jump in between these three phases rather than just these two phases. So then let's look at the theory. So I mean, all this empirical evidence suggests that for a generic nonlinear operator, it seems that the information processing power is the highest, the most optimal at the edge of chaos. So what's the theory behind this generic phenomenon? So so we started from, well, the famous, of course, ergodic theory, where it's known that the deterministic chaos just can be described using randomness. So this is the attractor of the dynamical system, dynamic operator. You have a deterministic part, and you have a randomness part. So the randomness part there is normalized with variance 1. So this sigma characterizes the variance, and that means exactly when sigma changes from 0 to a positive value, then your system becomes chaotic. So this is then, of course, also well known to be Landau's theory of phase transition. It just so happened that all the parameter here is the variance of the chaos. So then you can do some treatment, you realize, okay, actually then you arrive at this equation. So you applying Landau's theory of phase transition, you arrive that actually the phase transition from order to chaos happens when this is satisfied. So this is the Jacobian norm. This is Jacobian at asymptotic points, and F is F norm. So it's normalized by the dimension of the system. And this characterizes the edge of chaos. So in infinite dimension, when you apply random metric theories, you know that actually the spectral radius, which means the largest value of the largest eigenvalue of the Jacobian matrix, is 1 when this is satisfied. So when this is 1, actually the spectral radius determines the local stability. When it's larger than 1, it's locally unstable. When it's smaller than 1, it's locally stable. So the edge of chaos corresponds exactly to the edge of local stability. So these two are the same. But in any neural networks, no matter how large the dimension is, it's always finite. So of course, from the bottom, this result, you can see that actually they have also argued that for finite systems, for finite matrices, when this normalized Jacobian norm is 1, actually the spectral radius is larger than 1. And the smaller the dimension is, the larger is the spectral radius away from 1. But of course, for the modern neural networks, dimension is typically very high. So this result is these two are pretty close. But it means the edge of chaos doesn't mean edge of stability. Actually, the edge of chaos is at the edge of local instability. So that means.
Can you conclude in?
Yeah. So then, okay, I just conclude here. So that actually means you have this final phase diagram here, where the y-axis is the dimension, the x-axis is the normalized Jacobian. So the phase transition happens as the normalized Jacobian increases. Sorry. Okay. Anyway, so for infinite dimension, you almost only have two phases, where the middle stable periodic cycle phase is sandwiched in between. And here at edge of chaos, you have the largest periodic cycle, which each point on the cycle is a useful information point for you to represent information. And that's exactly why at edge of chaos, you have the largest stable periodic cycle, and you have the largest information processing power. So I'll just conclude here that the summary is both biological and artificial intelligence at the edge of chaos, and actually are due to the largest information content due to the largest bifurcation of cycles, which means there is the largest cycle length here. So metastable states are key to understand knowledge learned by AI and deep neural networks in general. So of course, this also relates to model generalization powers and how to improve the AIs through all these chaos techniques. Yeah, so yeah, I think I'm overrunning my time. Sorry about it. Yeah, sure.
On behalf of everybody, I applaud. You left a little, overshoot a little, so we can have one or two questions if somebody wants to raise hands or write down on the chat.
Okay, may I have a question?
Sure.
Sure.
Yeah, thank you. So, is there any difference? You mentioned a local stability or locally stable state. So, how to distinguish the difference between the local stability and the global stability? And the second question is about can we conclude if the system lies on a local stability according to the distribution of eigenvalues you showed in your slides? Thank you.
So yeah, so local stability is so you don't have to look at the eigenvalues distributions. You just need to look at the largest eigenvalue. So okay. If its norm is larger than 1, it's locally unstable. So okay. This is the bifurcation happens when the spectral radius is larger than 1.
So can we say the eigenvalue that the rho is higher than 1 is the dominant eigenvalue?
Yeah, so it's locally unstable.
Okay.
But then it can still be in the order phase, which means so you see these two. There's 2 points here. There is a green. Wait, do you see my screen?
Mm-hmm.
You see there's a screen. There's a green and there's orange.
Okay.
So these 2 points actually they come from the two very close by initial conditions, x and x prime, which differ by a tiny amount. So you can see at the end of the iterations, they're always together, right?
Yeah.
So it means it's order phase. They don't separate from each other. But in the chaotic phase, you see they're just further apart.
Okay.
So this is the case where here is locally unstable because it goes through the cycles, but it's in the order phase because the two initially adjacent points will just be adjacent to each other all the time. But here they are both locally unstable and chaotic.
Yeah.
I think that you guys should take this discussion further with your email. It's very interesting. Your discussion also, I hope it develops in a collaboration or a new paper that we will enjoy soon.
Right.
Fantastic.
Sure. Thank you.
So the paper is here. You can contact me. Yeah, we can discuss.
And also,
further.
I would like you to share your transparencies because they were not on full screen. So some people might have different difficulty in viewing. So if you want to share your transparencies, please feel free with the organizers.
Okay, sure. I'll definitely do that. Yeah.
Okay. Everybody also. So now we're going to the next talk, which is of Miss Premalatha, if I say correctly, Premalatha.
Yes, sir.
And she's going to to tell us about the different kinds of chimera states in a network of locally coupled Stuart-Landau oscillation.
Yeah,
So
yes,
the floor is yours. I will send you on the chat message every at 3 and 1 minute, so we can try to be on time. Okay. So now you have your 12 minutes to start with. Please,
okay, sure.
welcome. Can you share your screen?
Sir, I could not share my screen. Host disable participant screen sharing. It shows like that. Sir, I could not share my screen.
Yes, I don't know. Mihaly,
Can you now? Please try again.
Yeah, yes, sir. Now I can.
Okay. Okay.
Good afternoon, everyone. I'm Premalatha from PRG College of Technology, India. First of all, I would like to thank the organizer for giving me such a wonderful opportunity to present my research work here. And here I'm going to discuss the topic on different kinds of chimera states in a network of locally coupled Stuart-Landau oscillators. This work is done jointly with the Professor M. Lakshmanan, Dr. M. Senthilvelan, and Dr. V. K. Chandrasekar. This is my outline of talk. First, I will give a brief introduction about chimera state and its origin, and then I will discuss about basic coupling schemes available to the oscillators, and then I will introduce my model, that is locally coupled Stuart-Landau oscillator. Then I will discuss about main results, detailed analysis of dynamical states under clustering condition and dynamics under two different initial conditions. And finally, I will do my talk. It is a Greek word from different animals flying with a head of goat arriving from its back and the tail that ended in a snake's head. The term chimera has come to describe any mythical or fictional animal with parts taken from a various animal. So this picture depicts the ancient worker depicted in the intricate wall carving at Tarsaram temple, which is located in Tamil Nadu. And the above creature is a yoli. It is a mythical animal to keep away evil, who has the face of a lion and the body of a seahorse and the trunk of an elephant and the tail of a bull. And similarly, we come to the point. And similarly, the chimera state represents, it is a spontaneous breakup of identical oscillators that are identically coupled into two subgroups of oscillator. These two subgroups of oscillator having two different properties, which is indicated in this figure. That is, the edges of the oscillators are coherently distributed in space, and in the middle of the oscillators are incoherently distributed in space. So it has the combined properties of coherent and incoherent distribution of oscillators, so that it is called non-locally coupled oscillator, which is observed in a non-locally coupled phase oscillator by Chromoto in 2002. And chimera state occurs in the transition from complete coherence to incoherence, and initially non-local coupling is the necessary condition to observe then such kind of novel state, that is chimera state. And then from recent observations, we can observe globally coupled oscillators also show such kind of phenomena. And then later studies even relax this constraint, and locally coupled oscillators also show such phenomenon. So these are the basic coupling schemes available, which available to couple the network of oscillators. First one is the local coupling. Here the dot, each dot represents nodes of the oscillator, and here each nodes are coupled with its nearest neighbor only, so that it is called local coupling. And second one is the global coupling. Here each node is coupled with all the nodes in the network, so that it is called global coupling. And third one is the non-local coupling. It lies between local and global. And here each number of oscillators are coupled or number of oscillators in both directions, so that it R is called the non-local coupling radius. And chimera state is vastly reported by Komata et al. In 2002, and this Asia temporal pattern was named chimera Abrams and Strokens in 2004. We can also find the experimental observations in optical experiment, chemical experiment, and mechanical experiments, and so on. We can also observe the chimera state in nature systems also. And examples are unihemispheric sleep in many birds as well as dolphins. Sleep with one eye open. This means that what is the brain is and second one is the power grid network, and brain network, ventricular fibrillation, and pulse trends. And we can say many examples for chimera states. And this is our model to explore our results. This is the locally coupled Stuart-Landau oscillator. Here omega is the natural frequency of the oscillator, and C is the non-isochronicity parameter, and epsilon is the coupling strength, and here Z is the complex variable. It's Xg plus IYG. We are giving coupling only in variable. So next we discuss the detailed analysis of different kinds of amplitude chimera state. So that here in the present study we investigate the existence of transient amplitude chimera states, and also analyze how such amplitude chimera state becomes stable with respect to increase of non-isomorphism parameter. So to explore such a spatio-temporal dynamics of the system, about the system, we choose the cluster initial condition by choosing the system parameter values as omega is equal to 2 and epsilon is equal to 11. The first one represents the amplitude chimera state. So amplitude chimera state represents the coexistence of
we have a problem with the internet connection. Miss Premalatha, can you hear us? It's broken, I guess. Hello? Let us give some seconds for trying again. I think that, oops. Okay. Unfortunately, we have the standard Zoom technical problems. They appear in every conference. If you agree, we can let Ms. Premalatha conclude for her next 7 minutes later, if she can join us again. Could you please, Florian?
Yes.
Can you pick up from here?
Yes, sure.
And then we can see what happens with
Of course.
Miss Premalatha.
All right, I will try to share.
You're going to tell us about periodic motion in the chaotic phase of an unstirred Ferroin-catalyzed Belousov-Zhabotinsky reaction.
Exactly.
Which I am partial for that, because I guess you're going to talk about the oscillator.
Yes. It's mathematically quite similar. Yes.
Yes, I'm coming from the group of Brigos and Iniquities, so that's why I'm partial for that. It's a very important reaction, this one, a classic.
That's true,
Okay.
actually. Yes.
Okay. If whenever you are ready, please.
Yes.
Welcome.
I am ready. So thank you for the organizers for letting me give this opportunity to talk about our very new research results. We talk about the periodic motion in the chaotic phase of an unstirred Ferroin-catalyzed Belousov-Zhabotinsky reaction. Before I go into the details, I would like first to give a slight overview about what is actually chaos. And here, if we go to, according to Richard Kautz, it is the science of predictable random motion. But are there different types of chaos? So first of all, there are at least two different aspects of chaos. We have the statistical one, which is connected to the randomness, and there is also the deterministic aspect, which is normally connected to the sensitivity to the initial conditions. We look here at a very simple mathematical model. We have seen it today already. It's the logistic map, and here we have a parameter, this lambda, which for certain values goes to the chaotic regime. And we have here plotted from an application for lambda is equal to 4, the evolution of the system. And we can see here, if we look down, it is actually done for 3 different initial conditions, which are very close to each other. If we look in detail on the evolution, we see that in the beginning we have the same more or less evolution, but after some time they diverge. And this is what is normally called the sensitivity to initial conditions, and which is normally connected to what is called the deterministic chaos. But at the same time, in the same system, if we look split how to say, be seen as a random series. So we have here both aspects of chaos in the same system. Now, let's see if there are different types of chaos in different, let's say, natural systems. So to my knowledge, the first time when there was a natural system talked about chaos is when there was the transition to turbulence. It was a very important paper by Mihnea and Golub in 1978, where they, among other systems, were looking at the Rayleigh binary instability. And they found out this is actually the evolution of convection cells, which is here shown in a numerical simulation. And it was shown there that there is a transition to a turbulent state, which can be seen as a transition to chaos. And it can be characterized, which is one way of characterize this transition, is by looking at the Fourier spectra. And if we look, for example, here in this line, the velocity component of the field, the velocity field, we can see here a periodic change of the velocity. And this can be plotted in the Fourier spectra, and we see one main frequency and the harmonic repetition of this. So this is a clearly harmonic signal, a periodic signal. And we look at the same thing in the turbulent state, we get a less periodic, and we get the appearance of different more frequencies. So we are actually here on the transition to a chaotic state. So this is to say, what are the different possibilities to characterize chaotic transition. Our system of interest, we are working on this system since more than 10 years, is the Belousov-Zhabotinsky reaction. It is a chemical reaction system. It is a bromination of an organic species that shows a cyclic periodic color change, which is due to the catalyst, which is ferrin in our case. We have two different setups we can look at in this system. We have the Beaker setup, which is a bulk solution, where we have a periodic color change of the completely bulk solution. And then we have also the same system, but in a shallow Petri dish, where we can see the formation of chemical waves. It was discovered in the 50s of the last century by Boris Belousov, and later further modeled by Anatol Zhabotinsky. I will not go into all the details of the reaction. If there is a question, I can maybe answer it later. Mainly, we have an oscillation between the two states of the catalyst, which is ferrin, which is the blue one, and ferroni, which is the red one. So what is it about the chaos in the Belousov-Zhabotinsky reaction? In the very beginning, it was not clear if there is even a chaos possible in the Belousov-Zhabotinsky reaction. But in the early 80s, it was discovered that there is also a temporal and a spatial type of chaos. What does that mean exactly? So let's see first the paper by 82. We see if the system is constantly stirred. We see that there is, of course, because of the stirring, no convection and confusion taking place. So we have only a temporal evolution of the color change. So we have only chemical reaction going on. And it was shown that in this system, there is a transition to chaos possible. At the same time, a bit later in 84, it was even shown that in a Petri dish setup, such a transition to chaos can also take place. Here we have no convection because the space is so shallow that there is inhibited the convection. So what would we do actually measure in the Belousov-Zhabotinsky reaction? We measure the color change, and this is normally done by photospectrometric measurements, where we send a light beam through the solution and we record the transmission or absorbance of the situation. And this periodic color change is then registered as a periodic change of the signal between the blue down and the red up. And this change of the color is in our system, which is not stirred and open, then after some time going to a chaotic state. Around 2010, we discovered that this state actually is just a transient. So we have here a transient behavior, a chaotic transient, which comes from one periodic and goes to another periodic change. Some researchers call that a type of rebirth. Later then we have discovered that actually this effect was already discovered in the year 1996 by the group around Mauro Rustici and Nadia Marchettini in Italy. What is our configuration here? So for the effect I'm going to describe today, we have chosen a very specific cuvette configuration where we have a very quite slim cuvette with 2 times 4 centimeters and the width of only 0.5 centimeters. We followed the system with the webcam and we extract from the recorded video the green channel, which has around the peak sensitivity, which is important for the Ferrin around 500 nanometers. Now here we can see the time series extracted from the video, which shows the behavior which we actually would have expected. So we have a first periodic phase, which is shown here and magnified down here, where we have around 100 seconds of periodic motion. And then it goes in more or less a chaotic motion of the color change. And here in the meantime, somewhere after 3000, we have also zoom, where you can see this is a kind of chaotic system evolution. What I have done also is to look at the Fourier spectra of these regions to verify if we are really in a chaotic state. And what we see here is if we look at the first periodic phase, we can clearly see also in the Fourier spectra that here we have a main peak and we have the repetition harmonics of this main frequency, which is around 12.5 seconds. Down here is a bit later in the chaotic phase, and we can see here is not anymore ordered pattern recognizable. And also if we look at the power, it's around 300 times smaller than this peak. So it is more clearly a chaotic behavior. If we look a bit later in this space, which is shown up here and also later here, we can see not a really distinguishable motion, which in fact shows more or less the same properties of more or less chaotic motion. So this is more or less what is already known. We already expected that, but the interesting thing which we have observed in this specific cuvette is that there is the formation of convection rolls. And now I'm going to jump to the video. Let's see if it is working. Okay. So, is the video visible? Also the...
Yes.
Okay, then I will start. So in the beginning, we have a kind of periodic motion. We have the formation of bubbles, which are seen here in green. It's a wrong color image to better make the contrast of, to increase the, and now here we see already the convection cells. I hope you can also see them. This is around 50 times faster than the real time. And we see here the two different convection rolls, which are interchanging and sometimes become the same size. And in the end, we have only one convection roll visible. So there is an interchange between this behavior. And this behavior is, up to our knowledge, the first time that we see a periodic motion in a state which is actually characterized as a chaotic state. Okay. So let's go back to the presentation and see where we exactly see this. So we have 3 times of convection rolls configuration visible. We have the 2 convection roll configuration and the 1. And in between, we have a transition state between a small upper and a bigger down. And if we look at at which time point these oscillations are taking place, we see it here. We start with 1 convection roll, which then goes transiting to a second, 2 as a parallel convection rolls, which then again here must be some kind of transition and we come back. So it's a kind of oscillation between 2 convection rolls and 1 convection roll, but all within a chaotic transient. So if you just look at the color change, you would never imagine that in this state, there could be also a periodic motion visible. If you would, for example, we have not done yet this, but if you look, for example, at the velocity field throughout the line in this situation, probably you would observe a periodic motion. At least it's visible to the eye. I hope you have also seen this. So let's come to the conclusion. First, I was talking about chaos if it is a random motion. We have seen that in a very simple system. It is the logistic map that yes and no. It can be deterministic and it can be also random. It all depends on how you look at the system. What we have also seen, it is difficult to identify and characterize chaos. And very importantly, at least for us, it was very interesting to see that chaos is always very important on how you look at the system. You can even have a periodic motion in a so-called chaotic state. So now at the moment, since this is a very new findings, we tried to work on a numerical model to simulate the behavior we have observed in our system. At the end, I would like to shortly introduce our group. We are a living systems research. We're a small private research institute, and we're doing research in Austria, in the south of Austria, in Klagenfurt. Thank you for your attention.
Great. Thank you, Florian. That was very nice, on time, and quite interesting. Open the floor. The floor is open to questions. Anybody wants to raise a question? It was very clear and concise. I would like to ask about when you say about new techniques that you are developing for finding periodic orbits within chaotic regime in the data. Does this entail developing time series analysis technique where you can extract periodic orbits?
Well, I think it is, well, we're not working on that at the moment. Let's go back to the yes here. We say more or less the following, that yeah, here we see a kind of chaotic Fourier spectra. Mm-hmm. And we cannot actually extract the information of periodicity, because here we just look at the color change, and the color change in the system, when it is in this state, is in fact chaotic. But what would be probably a way to detect this type of periodicity in this phase would be to look at the velocity field. But for this, we have to think about how to experimentally get the velocity field, because so far we are just looking at color change. We have no other means of observation. Yeah.
Yes. There are techniques like symbolic dynamics or entropy analysis that they might be helpful.
Yes, we should. We definitely should look into this also. Maybe we will get something out of it. Yes, yes, it's a good.
Very interesting, because this is also extremely important, because just to remind you that this kind of forgotten chemical reaction was a shock at the community in the 50s and in the 70s, and also it was this kind of electrochemical reaction that triggered Ressler to develop his mathematical models and help launch the Ressler and Lorentz, the two attractors that launched the revolution of chaos. Yes. So thank you very much again. That was very, very good.
Very good. Thank you.
And now we have again a problem with Miss Premalatha. She's not. She appeared.
Sir, can I continue my talk?
Are you there? Oh, there you are. Okay. Can we try for the next 8 minutes?
Can I share my screen?
Yes, please go ahead. 8 minutes for you, and please open a little more your volume if it's possible. We can hear a little clearer. So you have your 8 minutes. Can you share the screen? Could you please share the screen? Miss Premalatha, are you there? Oh well, sorry for that. Let's continue with our next talk with Franziska Peter.
Okay, yeah, I'm here, Peter. Hello.
Hello. So she's going to talk about fluctuations in systems of couple oscillators that induced microcorrelations, and I have the feeling that she's going to talk about the Kuramoto model on this thing.
Okay.
I sneaked on your abstract, so
Mhm.
yes, and another important issue, microcorrelations in large systems. Please.
Thank you very much for the introduction.
12 minutes. I will notify in 5, 3, and 1.
Thank you. Okay. I first sent you a link because I share some videos, and in case you can't see them well, you can find them on this link. Okay. Now I share my slides. Okay. Well, okay. Sorry. Okay. Okay. Hello. So, as said in the introduction, you can't see it anymore. I'm sorry. I'll do it again. Sorry. 1 second. Now you can see the slides, right?
Yes. Now yes.
Good. Thank you very much. Okay. So, as said in the introduction, I will talk on how intrinsic finite size fluctuations lead to correlations in systems of coupled oscillators, especially in the Kuramoto model. My name is Franziska Peter, and I collaborated in this project together with Chris, Arkady, and Dennis. And now I'm in postdoc in Barcelona. So the interesting thing about systems of coupled oscillators, no, my slides don't go on, is that they capture ensemble synchronization, which is found in many biological systems. And the most prominent model that distills this phenomenon of ensemble synchronization is the Kuramoto model. So my slides aren't going on. I'm very sorry. I don't know why.
Don't worry.
Yes, now. Okay, sorry. Okay, ensemble synchronization. So this is very well described in the Kuramoto model. The Kuramoto model is so prominent because it has a solution in the infinite limit, self-sustained. And I will shortly guide you into the model for those who don't know it yet. So there are phases theta. And when they are uncoupled to the other phases, then they run with natural frequencies distributed to a natural frequency distribution G of omega. And then we couple them with a weak coupling, n of them, or now we go to the limit or n to infinity, and they are coupled with sinusoidal coupling. And this is because this promotes the minimization of phase differences. So it actually leads to a synchronous state. And also, this form of coupling is inspired by a spin model, and it allows for the self-sustained solution. And just as in the spin model, you can write down an order parameter for the system. So Kuramoto defined an order parameter, this one, which is 0 when all frequencies, when all phases are distributed symmetrically around the unit circle, and which is exactly 1 when all phases are exactly equal. So, so when we increase this coupling for any frequency distribution with compact support, there exists a coupling strength, critical coupling strength, above which oscillators are either in a synchronous solution or they rotate asynchronously. So there are two, there's one cluster of synchronized oscillators and 3 rotating oscillators. So the most decisive difference in finite size systems is that, like in finite spin systems, the order parameter fluctuates also below the critical coupling. So there's a finite mean value of R also below the critical coupling. And now we want to take a look at these systems. I hope you can see the videos now. And below coupling, the order parameter just strays around 0. And then when we increase the coupling strength above the transition, there's a synchronous cluster which basically stays together all the time. And there are some oscillators that do phase slips and turn around. And then if we go even higher with the coupling strength, then all oscillators lock and maintain a constant phase difference. So all these different coupling strengths are shown together here in one picture. So this is the order parameter, how it fluctuates at different coupling strengths for a random Gaussian distribution of natural frequencies. So you see that it rotates, and you see that with increasing coupling strength, we have a higher mean value of R, and the fluctuations get smaller. Okay. Another feature that you should know about for the fluctuation part of this talk is that the transition to synchrony depends strongly on the shape of the natural frequency distribution. So when the natural frequency distribution is uniform, then we have a first order transition to synchrony. And if we have more peaked distributions, then the central oscillators start to synchronize, and then the slower or faster oscillators join consecutively. And this tendency is also true for the finite case. So what I told you now was the dynamics of the macroscopic variables, and we need that to understand the effect of this fluctuating macroscopic variables on the single oscillators. And we will see that this effect is an ordering effect. So we somehow need to disentangle the fluctuating order parameter from the oscillators that form it. So this is the model that we saw before, the active oscillators that contribute to a fluctuating mean field. And now to disentangle them, but also to be able to zoom into smaller frequency differences, we let this fluctuating mean field act on passive oscillators. Okay, now I'll show you a video which you can see on this website that I shared. Here, so on the left upper part, okay, it's not showing, that you can later see it on. Okay, so you see here the synchronous cluster of the active oscillators, and then into this narrow band here, we put a lot of passive oscillators with very small frequency difference. So this is the whole range of passive oscillators' natural frequencies. So they are very close to each other. And then we see how these fluctuations actually order them, because they are not coupled to each other. They there's just the same fluctuating mean field acting on them. Okay. So yes. Okay, so we actually want to measure that. We don't only want to look on videos. And in order to measure that, we need to define a circular measure that describes correlation. And this is nicely done by this synchronization index. But also, we need to be careful, because all these oscillators will stay longer in the bottleneck caused by the central cluster. So we actually need to transform this away. And this can be done by a Möbius transform. And here I simply show that this Möbius transform is successful. So after the transformation, the transformed oscillators rotate more uniformly and don't do these fast phase slips. And then we can look on the synchronization index. So this is really the central part of the numerical experiment. So we take passive oscillators in pairs, and their natural frequencies have different frequency differences. So either they are very different or they are much closer to each other. And then we put them into the mean field caused by these active oscillators here. So those are the natural frequencies of the active oscillators. And you see that, for instance, the passive oscillators lock to the active oscillators, and this is why you get a very strong correlation. And what's interesting for us is more this region between those locking regions, and this is actually the central locked cluster of the active oscillator. So we are looking on the positive frequencies. Yeah, so on the kind of on the right-hand side of this distribution. Okay, and now we see that the fluctuations really cause some correlations. And in order to kind of single out this effect, we contrast it with an analytical model. And in this analytical model, there's only one important parameter, which is the ratio between the frequency difference of the passive oscillators and the size of fluctuations, so the diffusion parameter. And this analytical model just simply like it's a white noise model, so we compare it to white noise. And the order parameter has then this form, where these are Gaussian white noises. And we also Möbius transform them, and then we look on the difference of the Möbius transformed variables and their sum. And we see that this is actually a very slow variable, because the passive phases have very small frequency differences, so they will rotate very slowly in comparison to the sum of these same phases. And we can use that because we will now write a Langevin equation for these phase differences in phase sum, which corresponds to a Fokker-Planck equation. And then we can apply multiple scales analysis. So we can use that we know that this rotates slowly and this rotates fast, and then we can distinguish these two types of equations. And this Fokker-Planck equation, which then results, has a stationary solution. And by a little trick, we find this this nice analytical solution, which only depends on this parameter d that I just showed. So on the ratio between the passive oscillators frequency difference and the intensity of noise ratios. So you saw the Gaussian case, but also the equidistant case is quite interesting, because I told you that it's a first order transition. So the fluctuations are much stronger close to the transition. And we are here looking closely below the transition to knee. So fluctuations are very strong. And then you see that here the passive oscillators range in the same region, so to say, as the active oscillators. And you will see that there's no real central synchronized cluster. There's no oscillator that's really locked already. And the fluctuations really span across the whole region. So there's also very interesting, but it would correspond to a different analytical model, let's say. So now you shortly saw a more or less synchronized second, but it's destroyed again. Okay, so to conclude, we identified that the deterministic fluctuation, so it's chaotic motion of the active oscillators, induces order in the passive oscillators, and we quantify that by a synchronization index, and we can contrast it with an analytical solution with this model. And you find the things that I told, so that this first introductory part is in this paper, and then the fluctuations part is in this publication. So thank you very much for your attention, and I hope you were able to see everything, and I'm open for questions.
Okay, congratulations. Thank you. Very interesting stuff. The floor is open to questions. Anybody would like to ask something? I would have a short question about the transition where you made the Langevin equation in the Fokker plan. So what is the assumption that allows you to add this random variable? Is it
The random variable is kind of like the most simplistic model, how you could replicate the fluctuations. So it's just like instead of the real chaotic motion of the order parameter, like the circling motion, we just say it's white noise. So we compare it to a white noise effect, and we see that it has the same scaling law.
Yes. Yes, sure.
Yeah.
Okay. Because chaotic motion is into one-to-one correspondence with the Bernoulli process. If it is coarse-grained. So anyway.
So you are asking why we didn't use a Bernoulli process, so to say?
Yes. So this random variable is a Bernoulli variable.
Yes. Okay. Yeah, I mean.
Or could be.
Yes.
What I'm discussing, what I'm trying to say is that the assumption behind the probability distribution of your random variable comes from a phenomenological or an idea of your model.
It's a modeling idea. So it's, so to say, the simplest model that still describes the effects. So in the Einstein fashion, always take the simplest model that still describes all your features.
Great.
Yeah.
Well said. Anybody, thank you again. It was very nice, and also thank you for providing the supplementary information. That was very helpful.
Thank you.
Anybody else would like to John Doubledam asks, what kind of application do you have in mind to Franziska?
What kind of? So there are two interesting things in these types of problems. So on the one hand, most realistic, anything that you have in the lab will be finite. So the thing that I showed in the first slide, so this ensemble synchrony, I will just share the slide again. I hope it works quickly. So this is, for instance, from a lab that looks on yeast cells on a petri dish, and they see synchronization between these yeast cells. And this they want to understand whether it's really quorum sensing or whether it's rather a chromotor type of transition. And so this is a prominent finite size model in the lab where they really investigate the finite sizedness, which I think is very important in a lot of biological systems. So they are usually not infinite, and they also most of the biological systems are also temporal. So for instance, the mating fireflies, they see only a small region around them, and if they move, then they have small local networks that might be more or less all-to-all coupled, but they won't see the whole community at once, so to say. So this is kind of like the application side from biology, let's say. And in mathematics, it's also very interesting because it's not so clear how we come to this infinite case. So how do we come to the Odd-Antonsen manifold? So why is it stable? And the fluctuations actually give a hint. How is it stabilized in reality? So that would be the two applications, I guess.
Thank you.
Thank you for the question.
Yes, I would add that another application will be to detection of weak signals before complete synchronization, which is kind of interesting also.
Mm-hmm. Could you extend a bit? So because I don't understand.
Weak signals before bifurcation or phase transitions could be detected by ideas based on your model, but I'm afraid we can discuss that much more because once again, Miss Premalatha is here.
Thank you very much for your questions.
Thank you. So let's try again for another 8 minutes. And Miss Premalatha, can you hear us? Can you hear us? Could you unmute yourself? Unmute yourself, please. Okay.
Hi, sir.
So can you resume from where you left?
Yeah, yes, sir. Yes,
Okay,
sir. I will
please.
continue. Yeah.
Share the screen. You have
Can
8
I share my
minutes.
screen?
Yes, please.
Yeah, yes, sir. Can I share my screen?
Yes, please, go ahead. Okay, we are back. You have
Yeah.
8 minutes. I will notify you in 3 when you are before me. Okay.
Yeah, okay, sir. Okay.
Go, go.
The first one represents the amplitude chimera state. So amplitude chimera states represents the coexistence of two different domains. One is oscillating spatially coherent, and another one is spatially incoherent amplitude. While the average frequency of the oscillator, average phase velocity of the each oscillator in the system are phase rate represents here synchronized oscillators oscillating zero as a center of rotation and synchronized oscillating increasing value of the non-isomers. So the amplitude chimera state here. Coherent domains are not completely synchronized, where we can observe spatially two counter-moving domains starting from the middle of the coherent domain, which is illustrated in this spatio-temporal pattern, and the corresponding phase rate is given here. Interesting states disappear at large and small amplitude oscillations while and result in imperfect break chimera state. Actually, the state represents the fact that the coexistence of synchronized oscillation with large amplitude of oscillation and synchronized oscillations with small amplitude of oscillations persists for certain time, after which synchronized group becomes desynchronized and vice versa. This tendency repeats with the time but irregularly. It is also to be noted that the oscillator belonging to incoherent group switch to coherent group, but not necessarily the same group of coherent or incoherent oscillator become incoherent or coherent. Hence, this state is designated as imperfect braiding chimera state. This is different from imperfect traveling chimera state. So here we are leaving the transient time as 5 into 10 power 3 time units as a transient, and then next.
I think we lost connection again. What I would propose is to send the transparencies to everybody, like Miss Franziska Peter did, and have an interaction after the conference, because now we are getting a little too much of failed attempts. Can you? Okay. She's not there. Okay. So we have another 3 minutes to resume and say goodbye. If anybody would like to share screen and open and unmute, it's very welcome. Please do that, as many as possible, so can even have a family photo, a family screenshot. Okay. Only Florian is and Mihnea. Okay. Franziska, Mihaly, thanks, Ling, Geza, hi. Mihail, chief organizer. Okay. Maria, Dania, Jason, Kostas, Konstantinos, Johan, hello. Come here. You don't want to have a family picture. Okay. So anyway, I would like to thank all of you, and especially The organizers, which are represented by Mikhail Kanetidis here from the Aristotle University of Thessaloniki. And I personally, I enjoyed it a lot. I mean, all the talks were, well, except one which is virtually, somehow she will make up for that. I hope sharing by transparency and getting in touch with you all. I found the talks of very great, good, well, top quality, honestly, and very also informative, not only for what has happened in the past, the glorious past of chaos and complexity, but the challenging future, which is amazingly rich, especially with the advent of data science and new materials, where electrochemistry will play definitely a great role, and data science provides a fertile ground of trying to identify all the structures out of chaos, out of noise or whatever. So it was a pleasure for me. Please share your thoughts, or if you want to ask any other questions to the participants. For me, I thank you, and it was an honor to have me to be here with you all. Thank you very much. So
Thank you.
Thank you
Thank you.
for hosting.
Thanks a lot.
okay, so I'll take a screenshot just for the fun of it, and I will put it to there. This is for the party. I will send it to the organizers. So okay, that's it for today. Thank you all again, and indeed, I was honored. Thank you very much. Bye, everybody.
Bye.
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 Bye, Florian.
Bye bye.
Nice talk. I know.
Thank you.
Okay. Michalis, Maria.
Miss Premalatha is here again, but it's late now.
Too late for that. No, it's impossible. So
Yeah.
Michali, you take the shot and close the
Okay,
connection.
I'm closing the meeting. Yes. Goodbye.
Χαιρετισμούς στην Θεσσαλονίκη.
Ευχαριστώ.
Απειθή έχω τελειώσει, γι' αυτό.
Είστε από εδώ. Και κάποιοι από εδώ μου είπαν σας ξέρουν από τα θερινά σχολεία. Είσαστε στα θερινά σχολεία στο χάος.
Ναι, από το πρώτο, 30 χρόνια.
Μάλιστα. Ωραία. Έγινε, γεια σας, χάρηκα που σας γνώρισα.
Εγώ ευχαριστώ πολύ και εγώ για χάρηκα. Γεια σας.